Hello, everyone. Welcome to the Virtual Science Cafe, brought to you by the North Carolina Museum of Natural Sciences. I am your host. My name is Chris. I'm curator for the Daily Planet Theater at the museum, which is the big globe part of the museum. But right now, in the times that we're in, the museum in downtown Raleigh is closed, but that does not stop us from bringing you all the great science and nature content that you know we bring. That's right. Every Thursday night, we bring you our Science Cafe. It's either in the Daily Planet Cafe in better times, or it's right here on the internet. Tonight, I am so glad that you joined us. Thanks for tuning in. I hope that everybody is doing well. I hope that you're staying safe out there. Thanks for joining us. We've got a great show for you tonight because the one, the only, the extraordinarily talented David Allen Sibley is with us tonight. Now, if you tune in every week and maybe you're not 100% sure what's going on, Sibley probably flipped a little switch in your brain. You've probably heard this name before. If you've seen one of the many Sibley field guides, yep, it's that David Allen Sibley who's joined us for tonight's show. Author and illustrator, winner of birding awards from the American Birding Association. He's written a new book, What It's Like to Be a Bird, From Flying to Nesting, Eating to Singing, that is on shelves now. In fact, you can visit Quail Ridge Bookstore's website, right? Our local bookseller in Raleigh. They've got copies for sale that are signed. You can get a book plate copy as well. Make sure you do that. I'll drop a link in the chat box in just a moment. But let's bring him on. David, welcome to the Science Cafe.
Hi, thanks. It's great to be with you.
Thank you so much for joining us. How are things in your part of North America?
They're good. They're good. We're sheltering here. We're lucky to be sheltering on our house is on an old farm, so we've got a lot of space to walk around and look at birds and enjoying the spring migration.
Oh, that sounds lovely. I saw some maps recently that we're sort of like right at peak season for spring migrations. What's it like up in Massachusetts where you are?
Yeah, it's been really busy. This is We're right in the peak now of birds migrating. Well, all the small songbirds, the ones that eat insects that have to spend the winter in Central and South America, now they're migrating back north to here and beyond up into Canada. And just thousands, millions of birds are passing through right now. So it's just a really exciting time. Every day brings something different.
That's incredible. So when you go birding, do you have your field guide with you just to make sure you spot them right?
I don't, I don't
I think you
actually
probably
carry
know
it
them
with
at this
me.
point. I think you probably know them after, writing the books and all, and sitting down and meticulously and beautifully illustrating all of them as well.
Yep.
I think that's
Yeah.
something that makes your field guides so special are the illustrations versus the photographs.
Yeah. Thanks. Yeah. I mean, the illustration allows me to show an average individual of the species. So I can kind of condense all of my knowledge into one image, whereas a photograph is just showing you a snapshot of one individual bird, not an average of, or sort of a typical bird of the species. So yeah, I think illustrations, it's a really important medium, and I think there will always be room for illustration in the world, and for artists who do illustrations. It's just a very important way of conveying information.
And there's such a rich history of scientific illustration as well
Yeah,
that modern work can still feed into.
yeah, yeah.
So your latest book, What It's Like to Be a Bird. Now, this isn't another field guide, right?
Yeah, it's a book about what birds are doing and why. And it really um, I set out to try to answer a lot of the common questions that I hear about birds. And along the way, just started learning so many things. discovering just by reading research, trying to answer these questions, find the answers to these questions. I discovered all this information that was not readily available, and things I didn't know after a lifetime of watching birds.
Well, I think we should go ahead and get started. Everyone, David Allen Sibley, take it away.
Thank you. All right. Well, I'm going to share my PowerPoint slideshow and tell you about the book. And there you should be seeing a chimney swift on the screen. So, like I said, this book, one of the things I set to do in this book was to answer a lot of the common questions that I heard about birds. But the real beginning of this book was an idea for a book for kids, a book about birds for kids. So I wanted to feature all the most common familiar birds in North America, and also to explain something about them, their abilities, their adaptations, the things that they do. And as I got into the research, learning about those things and trying to answer all these questions, what I was learning was so amazing, so fascinating, and so eye-opening to me that it became those essays, that information became the whole book. So instead of being a guide to familiar backyard birds, it's a guide to what birds do, featuring familiar backyard birds. And beginning with the chimney swift, well, in the slideshow is beginning with the chimney swift. The book begins with geese, but I wanted it to be a kid's book. So some of the what I liked in books when I was a kid was big, colorful illustrations of very active birds doing things, really dynamic paintings. So I tried to channel that, sort of my 10-year-old self, and come up with paintings like this of a chimney swift high over the forest, trying to imagine what it might be like to be a chimney swift up, 3,000, 5,000 feet up above the earth, just flying all day long. And I learned that there's some evidence it's possible that chimney swifts are spending the entire winter in the air. They winter in South America. So once they migrate south from the chimneys where they nest in eastern North America, it's possible that they don't touch the ground, don't touch anything solid until they come back the next spring. And here's really channeling my 10-year-old self with a western kingbird attacking a red-tailed hawk in flight. And I tried to do these paintings. I wanted them to appear life-size, roughly life-size in the book. So I did the paintings at double life-size. That was the easiest way to measure, to keep the measurements right. So I have one of those paintings here behind me, this pileated woodpecker. That's double life size. And then when it's reduced to 50% in the book, it appears at life size. And I got to do a lot of really fun illustrations like this one. This is pretty self-explanatory, a race involving a roadrunner and a coyote and a few other competitors. And there's more explanation in the book. But it was a lot of fun working on this book. And I also wanted to feature birds, familiar birds like cormorants, but most people don't really appreciate cormorants. You don't unless you get a really good look at them. But cormorants are beautiful. They're incredibly colorful and ornamented with little blue dots around the eye, and that intricately patterned bill. So I really wanted to feature the birds at their best. Here's an example of one of the questions that I tried to answer. Why do birds take baths? And the obvious answer is to get clean, which is probably part of it, but I learned from the research, from the published research, that there's um, another reason is that water reshapes their feathers. So uh, if a feather gets bent, apparently all you have to do to straighten it out is get it wet, shake some water off, and let it dry, and it will dry um, back in its normal position without the bend. And it's just like us waking up in the morning with bedhead, with our hair sticking out at odd angles. We take a shower and brush our hair, and it dries straight the way it should be. Um, Birds do the same thing. They take a bath, they get all their feathers wet, and then they preen to put all the feathers in the right position, the right alignment, and the feathers dry just the way they're supposed to be. So that's probably one of the main reasons that birds take baths, is just to fix their feathers. So I'm going to talk for the next few minutes about this bird, belted kingfisher. This is a really familiar and popular bird that anyone can see anywhere in the lower 48 states. In Canada, they're really widespread and conspicuous. And the way they catch their food of fish is to hover over the water. So they'll hover 20 feet, 30 feet above the water and look down into the water until they see a fish. And once they've targeted a fish, they'll dive straight down, headfirst into the water, plunging in with a big splash and grabbing the fish, hopefully, in their bill. Um, so if you watch a kingfisher while it's hovering, um, you can see that they're hovering by flapping. They have to flap and fan their tail and sort of wave. The body's moving around, adjusting to air currents. Um, it's a lot of effort to hold their position in the air. And through all of that, their head remains perfectly still, absolutely stationary, fixed at a point in space, even though they're suspended in midair and their body's bouncing around and tail flaring, wings flapping, all that activity below the neck, and the head stays perfectly still. So I'm going to talk about all the things that go into that ability, because it brings up some of the amazing adaptations of birds. So the kingfisher, first, it has to be able to fly. It has to breathe to keep its muscles oxygenated while it's making all that effort. It has to be able to sense the air currents around it. It has to have a sense of balance of what direction its body is moving, where its body is, so it can adapt to that motion. Vision is a really important part of all of this. And then just the physical ability, the muscle and skeleton ability to make the adjustments, to accommodate for all the body movements to keep the head still. So going way back to 160 million years ago, this is one of the ancestors of birds. This is a dinosaur called Ankisaurus that lived 160 million years ago. And it had feathers. Lots of dinosaurs had feathers. And at this time, there were already quite a few birds with feathers. Um, and this dinosaur, Ankylosaurus, the fossil is so well preserved that researchers were able to look at the fossil under a microscope and see the melanin granules, the little pigment granules in the fossil, in the feathers. And by measuring those, looking at different parts of the fossil, they mapped out the color pattern of this dinosaur. So this is actually an approximation. It's my own approximation based on their research of what this dinosaur might have looked like, with a gray body, black and white, longer feathers on the wings, well, wings, sort of arms, legs, and tail, and a sort of reddish brown crest. Now, all the dinosaurs were wiped out by a meteor that hit the Earth in the Yucatan about 160 million years ago. And all dinosaurs were wiped out, 75% of all species on Earth. That was such a cataclysmic event. And it's thought that only 3 species of birds survived that event. 3 species of small ground-dwelling birds. One maybe like a chicken quail, one like a tinamou, which is a South American species related to ostriches, and one who knows what it was like, maybe like a roadrunner or something like that, but that those 3 species gave rise to all 10 or 11,000 species on Earth today. So feathers evolved a long, long time ago, and feathers did not evolve from scales. They started as a hollow tube, like a bristle on the left. So this is a sort of a showing the stages in the development of feathers. A hollow bristle, and then the fibers that make up the bristle separate into a downy, fuzzy feather. And at this stage, dinosaurs with those kinds of feathers, the feathers were useful for insulation, and they could have also been colored either for camouflage or for display. The next stage in the middle, the feather branches. So it has a central shaft and many side branches. So that's like an ostrich plume today. But the side branches aren't connected to each other. In the next stage, each of the side branches develops tiny branches of its own, and those branches have hooks that hold those barbs together. So then the feather becomes a more solid surface. And then it really starts to become useful for things like flying. And on the far right, a highly evolved, really specialized feather. This is a long wing feather from a modern bird. And one of the upshots of looking at this, these stages in the development of feathers is that flight is one of the most recent developments. Feathers evolved long before, well, in forms that would not have helped a bird to fly, and gradually feathers evolved to have all of the specialized shapes and structures that allow birds to fly. Now, one of the things I learned that was really eye-opening to me in the process of working on this book is that feathers are waterproof because of their structure. I had always heard and assumed that the oil that birds preen into their feathers was what made them waterproof, but actually it's the structure. So this, you're seeing on the left a feather, and on the right a magnified cross-section of a few of the barbs on the side of the feather, and a droplet of water suspended on top of those barbs. So the spacing of the barbs is too close together for water to flow through. A drop of water has surface tension that holds it together as a droplet, and it can't fit through small spaces. So that's the principle behind Gore-Tex. A feather works the same way, and the barbs, the drop of water rests on the tops of the barbs, just barely making contact across the top of the barbs. So it doesn't stick to the barbs. It doesn't go through, it doesn't stick, it just rolls off. But that's almost entirely because of the structure of the feather, not because of the oil. So feathers are a really critical adaptation for flight, but so many other things go into the ability to fly. A bird's body is very compact and centralized, and all the weight, all the mass is in a compact shape right below the wings. So this is a pheasant in flight, showing the actual flesh and bones of the body with all the feathers. And you'll see that the wings are almost entirely feathers. The tail is entirely feathers. The legs are just thin bones and a leathery covering. All the muscles that control the legs and the toes are part of that central body mass. And similarly, the wings and the head is small, the neck is thin, the bill is a lightweight structure that birds use just to manipulate food. And so they don't have jaws and teeth that would be too heavy and sort of put them off balance by when the head is out in front of the body like this. If they had heavy teeth in their mouth, uh, they wouldn't be balanced in flight. So they've reduced weight at the extremities and consolidated all that weight in the center of the body. So when a bird eats, it doesn't chew, it just um, gets the food in its bill. Generally, they swallow their food whole, and in their stomach, they have sand, gravel, which is sort of a substitute for teeth. And as the stomach muscles squeeze and grind, that grit helps. It sort of acts like teeth to help grind up the food in their stomach, and so that they can digest it. But all that happens in the central body mass, not out at the extremities. So that's some of the many, many adaptations that have been necessary for flight. So the kingfisher is flying, and it's putting a lot of effort into flapping. It has to be able to breathe. And it turns out birds have a respiratory system that is completely different from ours, and apparently a holdover from the dinosaurs, or a gift from their ancestors, the dinosaurs. So this is a schematic of the lungs and air sac system, and I won't go into too much detail on this because it's complicated, but the lungs in the more purplish color here are rigid. They don't expand and contract like our lungs do. Their air flows through like coolant through a car radiator, sort of. And there's lots of surfaces for the gas to exchange, for oxygen to be taken out of the fresh air and carbon dioxide from the blood to be put into the exhaled air. And the way the air sacs work, a bird breathes fresh air on inhale and exhale. So we fill our lungs with fresh air, the lungs expand, we gather oxygen out of that air, and gradually the oxygen concentration in our lungs goes down. We have to breathe that air out and take in another breath before we get more oxygen. Because of the air sacs that store fresh air with each inhale, the birds, they inhale and fresh air is passing through the lungs. And when they exhale, fresh air comes from the rear air sac on the left here through the lungs. They're still breathing fresh air. So they have a continuous flow of fresh air through the lungs on inhale and exhale. And what it means is that a bird is essentially never out of breath. Their breathing system is so efficient that you'll never see a bird that's out of breath. If you see a bird that's panting after exerting itself, that's because it's too hot. They're not out of breath. They do have a problem with overheating, and the way they cool off is to pant. But their respiratory system is just incredibly efficient. Now, while they're flying, they're completely covered with feathers. The feathers are important for streamlining the body, so they move through the air easily. But they have to be able to sense what's going on around them, to sense the air currents, the movement of air around their body, so they can react to it. You would think that the feathers would insulate them from that, but they have these specialized feathers called phyllo plumes, which are illustrated on the left here. Several phyllo plumes grow at the base of every feather on the bird, and they're connected to nerve endings in the skin, so that as the feather moves, it moves the phyllo plumes, and the phyllo plumes send information about what every feather is doing. So the bird can sense constantly whether a feather is being like pushed down towards the body, high pressure, turbulence or pulled up from the body, or uh, everything that's going on around the bird, they can sense because of these phyllo plumes. And they have an incredibly sensitive um, uh, ability to feel the air currents around them. Um, they it's how the kingfisher can hover in the air uh, just to be able to understand how the air is moving around it, and how little gusts, little fluctuations in the air movement around the bird, a breeze, a little gust of wind, they react to that instantly by flapping, fanning their tail. All of that is being sensed through the feathers of their body, the feathers on their wings. They know how the air is moving and how to react to it to hold their position. It's pretty incredible. Um, Now, the kingfisher also has to have a really good sense of how its body is moving, um, to know what's going on, um, whether the body is moving up or down or side to side. Um, they have an incredible sense of balance, and all birds do. They can balance on a tiny twig, even while the twig is moving um, in the wind. And even while they're spinning their head around to look in different directions or to preen. um, It turns out another amazing thing that I learned in the process of researching this book. I had always heard that birds have a kind of automatic gripping mechanism in their feet, so that when they crouch, the tendons automatically tighten and clamp the toes around their branch so that they don't fall off when they're sleeping. It turns out that's not true. Um, they don't they don't do that. There is no automatic gripping mechanism in their feet, and when they sleep, they're simply balancing on the twig. They don't grip the perch at all. In fact, when they're sleeping, their toes are just loosely draped over the branch in a U shape. So the way I've illustrated this bird kind of tightly gripping the branch, that's something they do when they're active and moving around. But when they're sleeping, their toes just kind of hang loosely over the branch. So their sense of balance is like us. They have a balance sensor in their ear, in their head, that tells them how their head is moving. Um, but they have the advantage of an extra balance sensor in their pelvis, which is kind of on their lower back. So birds have a double sense of balance. They can tell which direction their head is moving, and at the same time, what direction their body is moving independently. And it's critical to all kinds of things that birds do. You know, if you see a bird standing on one leg and spinning its head around to preen its feathers, um, if you try, you can stand on one foot, but try standing on one foot and kind of swinging your head from side to side and turning your head around. You'll lose your balance pretty quickly, because your only sense of balance is in your head. The birds have an extra balance sensor in their pelvis that helps them to keep their body stationary. And the kingfisher is using that, I think, while it's flying, to understand how its body is moving and be able to react to that to keep its head stationary. Now, vision's another critical part of this, and bird vision is very different from ours. Um, Birds process visual information a lot more quickly than we do. So the flycatcher that's snapping an insect out of midair is um, they're seeing faster than we do. So we when we watch a movie or a video, those pictures, it's a bunch of still pictures flashing by at 30 frames per second, and it's too fast for our brains to react. So we see it as a blur, a moving picture. Birds can process images more than twice as fast as that. So presumably they would see one of our movies as a slideshow, a bunch of still images flashing by. And that ability is critical for birds to be able to fly like they do through tangled foliage at high speed, or for this flycatcher snapping an insect out of midair at high speed. And the flycatchers, it turns out, they don't just fly up and kind of fly through an insect and scoop it into their bill. They actually snap it out of the air with the tips of their mandibles. So imagine flying 20 miles an hour, following the path of a mosquito in midair and snapping it out of the air with a pair of tweezers. That's basically what the phoebe is doing. Um, Now, other birds, well, most birds have eyes on the sides of their head. Our eyes are on the front of our head. Both of our eyes focus on the same spot, and we see one point of detail, one tiny point of detail with both eyes. This snipe, with eyes on the sides of its head, is seeing 360 degrees around it. They can see in their peripheral vision the entire horizon, 360 degrees around, and the entire sky, all at once. And instead of seeing detail in one point, they see detail in a band along the entire horizon. So and that's where danger usually comes from. So they'll be watching for danger, and they use their vision almost entirely to look for danger. When they're finding food, they're using their bill, they're using the sense of touch and taste and smell to stick their bill into the mud and find tasty treats in there, while their eyes are watching their entire surroundings for danger. And what happens when a snipe sees danger is that it freezes, it crouches and freezes and relies on its camouflage and cryptic coloration. Um, so hoping that it won't be seen, and that's how it escapes predators. And because of their vision, even when they freeze and hold still to let their camouflage work, they can still see everything that's going on around them. So even while they're holding perfectly still, they can keep an eye on the predator, on any kind of danger that's around them. Now, other birds that do hunt by sight, like eagles and flycatchers, have a different visual system. They do have points of detail in their eyes, but they're still on the side of their head. So they're looking in different directions with each eye, and eagles see 2 points of detail in each eye. So a bald eagle is constantly monitoring most of its surroundings. They can see almost 360 degrees around with their peripheral vision. And then they're seeing 4 points of detail, two with each eye. So they're constantly monitoring multiple points of detail. And the strongest, their most detailed vision is out at about 45 degrees. So the way I've painted this eagle head on the left, that eagle is giving you its full attention. It is looking straight at you with one eye. That is how a bird studies something. So they don't have great vision straight ahead. Most birds actually can't see the tip of their bill. Um, but their best vision is to the side. So that's the same thing that robins do. When you see a robin hopping around on your lawn and it's tilting its head as if it's listening, but it's not, it's looking. It's using one eye to study something on the ground. And to do that, they tilt their head and aim that one spot of detail down at the ground. Um, so what the kingfisher is doing in flight is similar to what pigeons and chickens do when they're walking. Um, we say that pigeons bob their heads when they walk, but they're actually holding their head perfectly still in space while they walk, and then snapping it forward on the next step. So a pigeon moves its head forward to a position in space, and then picks up one foot and steps forward and moves its body forward underneath its head. But if you watch very carefully, you'll see that the head stays perfectly still while the body slides forward underneath it. And then when that front foot is put down and the back foot is lifted up, the head snaps forward to a new position and holds that position while the body moves forward underneath it. And in order, the reason pigeons do this is to monitor their surroundings, to keep a close eye on anything, especially anything that's moving around them. The way to see if something is moving is to hold perfectly still and watch for any change in your view. So that's what the pigeons are doing. And researchers found that if they put a pigeon on a treadmill, a pigeon walking on a treadmill where the surroundings don't change doesn't bob its head. It fixes its vision on some point around it and holds that view, holds that position, and walks without moving, without bobbing its head. Um, so, oops. The kingfisher in the air is probably fixing one eye on some point in its surroundings, or fixing one of its focal points of detail on something in its surroundings, and keeping an eye on that to help it as a kind of reference point, to help it maintain its position in the air. And at the same time, with other detailed vision, it's looking down into the water and studying fish, looking for the right opportunity, looking for a fish that's close to the surface and holding still enough to be catchable. Now, the last thing the kingfisher needs is a really flexible and responsive neck. And all birds have very flexible necks. The owls are known for their ability to turn their heads around. There's the folklore is that they can turn their head completely in a circle, which is not quite true. They can go about 3/4 of the way around, 3/4 of a full circle. But all birds can turn their heads more than halfway around. They have longer necks than we do and more vertebrae, and they're more flexible. And that is one of the things, the structural thing that allows the kingfisher's neck to act as a shock absorber. So as the body bounces around, the neck absorbs all of that motion, and so that the head can stay perfectly still. So we've gone through all these things: the flight, breathing, sensing air movement, balance, and the neck. Oh, and vision and the neck working as a shock absorber. But it's still, even after going through all of those things, I still find it just incredible that a bird can do this. To the senses and the reactions involved have to be so subtle, so intricate, so refined, to be able to absorb all of the motion of the body, to react to that with the neck and hold the head perfectly still. It's a really amazing ability. But it works. The kingfishers are very successful, and they can all do this. Young kingfishers can do this within days of their first flight. So that's just one example of something that birds do, and all of the different abilities that go into that. And one of the things that impressed me most as I worked on this book was all of the decisions that birds are making. So birds are they have a lot of their abilities, or their adaptations come through instinct. A young bird, just a few weeks old, can take off and fly on its species' normal migratory route and timing and reach the normal wintering grounds without any instruction from the parents. and it'll come back the next spring and build a nest without any instruction, only what it knows instinctively. But at the same time, there are all kinds of decisions that birds have to make all the time. They're constantly making a sort of cost-benefit analysis of, they're hungry, but there's a predator, but a storm's coming, and weighing all of the options and deciding when it's important to go look for food, which food is worth looking for, um, when to stay undercover, when to go out, and what to feed their young is another. It's partly instinctive, but also a lot of decisions. And it turns out, gulls are famous for eating garbage, literally. Gulls go to garbage dumps and eat what they find there. And they hang around fast food restaurants and beaches and eat whatever scraps they can find, French fries, leftover hot dogs. But when a gull is feeding its young, they'll go to the garbage dump to get food for themselves and then fly out into the ocean and catch fresh fish and crabs and take those back to feed the chicks in the nest. And chickadees are one of the most reliable and frequent visitors at bird feeders. They eat sunflower seeds and other things. But the adult chickadees, when they're feeding their young, they seek out insect larvae like little green inchworms. And for the first week after the young hatch, the chickadees feed them a large proportion of spiders, more spiders than at other times, and more spiders than they would find randomly. And it turns out that spiders are high in taurine, which is an essential nutrient important for brain development. So the chickadees instinctively know that spiders are a good thing to feed to their chicks in the first week after they hatch. And the Baltimore oriole is an example of a bird that builds a really intricate nest with no training, no instruction. The female oriole comes back just 10 months old, 11 months old. She comes back to the nesting grounds and can build a nest, but at the same time, she has to adapt to whatever materials are available and pick a location, find the right materials. And it turns out birds do learn about building nests. Their first nest, they get better at it. They make adjustments. They'll choose different materials. They'll build a thicker nest in cold climates for more insulation. So those are just a couple more examples of the kinds of things that I learned working on this book, and about how there's so much more going on in a bird's life than I ever imagined. I've always appreciated them, but I learned so much in working on this book. So I had a really good time creating this book, and I hope you have a good time reading it and exploring all the information that's in it. I hope it gives you a new appreciation of birds and at least some sense of what it's like to be a bird. And thank you for listening, and I'm happy to answer questions.
David, thank you very much. That was fascinating.
Oh, good. Thank you.
Absolutely incredible. Number one takeaway from me right off the top of my head, the part about the bird feet clenching the branch automatically.
Yeah.
I promise that a teacher told me that at some point. Like
Yeah.
that was up here.
Yeah, like I said, I had heard that my whole life, and it's, if you have a chance to handle birds like in a banding station or something, that it does happen. There's sort of pseudo confirmation, which I think is how that little bit of trivia got so entrenched. But I ran across this research from maybe 15 or 20 years ago, and it was someone had some starlings that they were doing other research on, and looked at them while they were sleeping and said, "Hey, they're not gripping the branch. They're just sitting there sleeping with their toes loosely hanging over the branch." So they looked
Right,
into it
right.
a little bit more and debunked the whole thing.
Fascinating stuff. And of course, the illustrations, the presentation itself is beautiful, full of your
Thank you.
illustrations. So, yeah, let's go to questions. As you predicted before the show, the questions have been rolling in
Okay.
faster than we could keep up with them. So I've got an enormous list here, but we've got a few minutes
Yep.
and we'll get to as many as we can. So I'll start at the very top, some of the early ones that we got early on in the presentation. What's the dividing line where a difference between a bird and a dinosaur? Is there a
Ah.
dividing line?
Um, there isn't really. It's gradual evolution. There are two. Now, I don't know a whole lot about this, but I gather there are two main branches of dinosaurs, and they're known as lizard-hipped and bird-hipped based on their pelvis structure. So all birds are descended from the bird-hipped dinosaurs. So not all dinosaurs are related to birds. There was an earlier split in the evolution in the family tree, where some dinosaurs went off in the lizard route, the sort of crocodile route, and others went the bird route. Um, but yeah, there isn't. I mean, the meteor, the 160 million years ago meteor, is a real dividing line where all dinosaurs ended and only a few birds passed through.
Right, right. Let's see. Eric is asking, what medium do you usually work in?
I most of my well, So all of my field sketches are done in pencil. That's what I use all the time when I'm out studying birds. And so it's just pencil and paper. The bird guide is painted all in gouache, which is opaque watercolor. For this book, I did it all in acrylic. Um, and I switched to acrylic when I did the paintings for my guide to trees. Um, because gouache, the opaque watercolor, it doesn't handle green colors very well, and it's hard to get the sort of satiny texture of leaves in gouache. So I switched to acrylic for that book, and then I liked acrylic enough and got comfortable with it and started doing some bird paintings. And I like the way it's more colorful, more sort of it has more weight than gouache in a way. So I, I I wanted to use it for this kind of book, this big, colorful illustrations of birds doing stuff.
All right, now a version of this question came in several times. Most amazing bird,
Oh.
followed by favorite, followed by least favorite.
Ooh, most amazing. There would be so many uh, candidates for that. I mean, hummingbirds have to be right up there as, I mean, they're the smallest, the fastest wing beats, the fastest heart rate, and the incredible feathers. Um, all of the bright colors on the hummingbird's feathers are iridescent colors. It's not pigment, it's the structure of the feather that reflects certain wavelengths. And I described the very basics of it in the book. It's incredibly complex. I talked to a few people about it, and I couldn't even really understand how it works. So I've described just the very basics of it, but it's essentially layers of structure in the surface of the feather that match the desired wavelength of light and reflect just that wavelength. So it's one of the most refined structural colors in all of nature. And uh, so I've put hummingbirds right up near the top of the most incredible birds, but they all do incredible things. And my favorite birds, again, I have a long list. Owls are always near the top. This time of year, the wood warblers, the warblers that are migrating back from the tropics and heading north, these little tiny birds that weigh, some of them weigh only 6 grams, where a nickel, if you have a nickel in your pocket, that's about 5 grams. So imagine a bird that weighs as much as a nickel flying 2,000 miles from Panama to Canada. Um, and then they're just so magical the way they show up this time of year. Suddenly, one morning, you wake up and your yard is filled with warblers and warbler song and bright colors. So they're all the warblers are among my favorites. And I'll
And
skip the least favorite question.
I couldn't imagine that you had a least favorite.
No.
So let's see here. Deborah Martin asks, was there any species that you wanted to or expected to include in this book that didn't make it?
Yeah. There, well, like any book, I always end up with a lot more information, a lot more things I want to include than I have room for. And it's a good exercise for me to kind of have to weed out or sort of cull the ideas down to just the best ones that will fit in the book. So the one I actually have a painting of a loggerhead shrike that was meant for the book and then didn't get included. There were quite a few species in the early drafts, the sort of outlines of the book. There were quite a few other species that I wanted to include, either as featured species or just sort of sidebar. And I had to limit it to this group, but the one that I actually painted and ended up not using is the loggerhead shrike. So maybe I'll find do a follow-up book and be able to use that sometime.
Find a good use for that one. All right. Next one. What about, let's see, you were talking about how feathers are sort of naturally waterproof. And Chris Jensen has asked, what about cormorants and anhingas who are not very waterproof?
Yeah. So yeah, those are really interesting, and there's still some debate about what exactly is going on. But so it turns out that the structure of a feather, the spacing of the barbs, wider spaces are better up to a point. Wider spaces are better to have water just roll off. So barbs spaced more widely means a drop of water will be in contact with fewer barbs, making less contact, so it will roll off more easily. But wider spaces means water can get through more easily under pressure. So species that dive underwater, like cormorants, tend to have the barbs closer together, so that water won't be forced through under pressure. And then all the land birds, like robins, crows, orioles, they have the barbs farther apart. So if you look at a feather under a microscope and measure the spacing of the barbs, you can actually tell whether it's a bird that dives underwater or just swims on the surface, or normally only has contact with water sort of incidentally through rain or dew, things like that. So anyway, cormorants, well, it turns out, I guess, anhingas have very wide spacing on their feather barbs, and water does go through. So anhingas, did I say that? Anhingas get wet. Water actually goes through their feathers and soaks the feathers and gets their body wet. So anhingas can only live where it's really warm because they would get hypothermic otherwise. And they actually sink. They don't float. They get in the water, they sink, the water is soaking their body. That's unique among birds. Cormorants, which are related to anhingas, but a different family, they actually have, their feathers are waterproof, So, and I've illustrated this in the book. The center of the feather has typical barb spacing for a diving water bird. So the center of each feather is waterproof, and then around that, the margins of the feather have the barbs have no barbules, so they're not held together. They're just loose, kind of fringe on each feather, and that part gets wet. That part gets soaked when a cormorant goes in the water. So they're waterproof. Water is not penetrating through the feathers to their body, but on the surface, the margins of the feathers are getting wet. Um, and that presumably allows them, it benefits them, maybe making them a little bit heavier so that um, they're less buoyant and they can swim underwater more easily. It might also help um, with friction in the water. Nobody really knows. But cormorants are the most efficient marine predator known. They catch more prey, more unit prey per time than any other predator in the ocean. So they're doing something right. And but they can only be in the water for a certain amount of time, and then they get too wet, too heavy, and have to hop out and dry off. But they're not. It's not because of oil. Again, it's not because of. I had always heard that cormorants don't have oil in their feathers, and that's why they get wet. But again, it's the structure of the feather, not the oil. And they are waterproof. They don't. Their body doesn't get wet, only the surface of the feathers.
Very, very interesting. Right. Let's move on to the next one. I think you mentioned this, comments about phyllo plumes and how they might function.
Yeah, yeah, those are the little tiny sensory feathers that are featherless, little, um, they're very slender, tiny little plumes that grow at the base of each feather and have a lot of nerve endings at their base. So that's what tells a bird when if there's a feather is out of place, if there's something stuck to a feather or a fly crawling on their feathers. The phyllo plumes are apparently what tells them that's going on.
Susan is asking, how did you learn to draw birds? And the comment, your drawing videos have been very helpful.
Oh, good, good. That's great. Thanks. Yeah, I started drawing birds. You know, when I was 5 years old, I liked to draw, and birds were my favorite subject, and I never stopped. Um, so I learned to draw birds just by drawing a lot of birds and looking at them. And every drawing is really a study. Um, it's a chance to kind of test your understanding of the bird. Um, so I spent many years just looking at birds, doing pencil sketches, looking at more birds, kind of gradually figuring things out, how the body is shaped, how the head moves, how the wings fold, all those things, and gradually through sort of trial and error experience, how to represent that on paper.
Lucia is asking, why do birds wipe their beaks back and forth on branches and fences?
Mm. Yeah, that I think it's just cleaning. They uh, they're obviously always picking things up in their bill and getting things stuck to it. They might have um, a little bit of uh, berry juice or insect guts or something, and that might be anything sticky on the bill is going to pick up spider webs and dust and fluff, and that's probably pretty distracting, even though they can't really see the tip of their bill, most birds, but they would see, the same way we would see a little uh, bit of fuzz stuck to our nose. It's probably really distracting. So I imagine that that's usually what's going on when a bird wipes its bill, is that there's something something bugging them, some little bit of fuzz or hair or something that's stuck to the bill, and they want to get it off.
Now, this is a good one, only because I see the drawing, the painting of the pileated woodpecker behind you.
Yep.
And Chris here is asking, they've heard that woodpeckers protect their brains with their tongues. Is that a myth?
Yeah, there's not a lot of support for that idea that the tongue, so woodpeckers, they have very long tongues, and the tongue actually wraps all the way around the skull. When the tongue can extend more than the length of the bill, and all of that length, when the tongue is pulled in, all of that length is wrapped around the back of the skull to the forehead. And I have some diagrams of that in the book. And also the question of why don't woodpeckers get concussions? There's been quite a bit of research on that. The two of the main reasons are just that there's very little mass involved. So their head and their brain are small and lightweight. So there's not a whole lot of inertia there. And also their brains are on the back of their head, oriented where our brain's on top of our head with a flat side across our head. Their brain is on the back, so the flat side of their brain is facing the tip of their bill, which means that there's a wider area to absorb the shock of hitting their bill against the tree. I guess those are two of the biggest reasons that woodpeckers aren't affected by all the hammering that they do. But there's also been some recent research that shows that they do have a lot of the evidence of brain trauma, that when you look at woodpeckers' brains, they do have the indicators of traumatic brain injury. So there's still some research going on with that. But it has been suggested that the tongue acts as a kind of shock absorber in some way, but I think there's not a lot of support for that.
So let's see. There's lots of comments of people having similar reactions to me to having some of these myths busted, like about pigeons bobbing their head.
Oh yeah.
So these are great. But it looks like we're coming close to the end of our time. So there was one user, Sweaty Skin Folds, great username, I guess. Asked, is it true that birds see in ultraviolet light? And what does that mean about plumage coloration?
Yeah, that's a great question. They do. Many birds, not all birds, but many can see ultraviolet light. So they're seeing a whole range of color that we don't. Like when a bird looks at a rainbow, it sees a whole extra band of color on the bottom of the rainbow. And there are a lot of plumage colors that have evolved as in ultraviolet range. So chickadee is a good example where we see chickadees as black and white. They have black caps and black throats and white cheeks. And males and females look alike to us, but apparently male chickadees have a lot of ultraviolet reflection from their white cheeks. So to a chickadee, it's really obvious when they're looking at a male or a female. Because of the ultraviolet reflection on the cheeks. To us, it's just they all look white, but if you're a chickadee, if you can see ultraviolet light, apparently there's a bright ultraviolet flash on the cheeks of a male. And lots of other examples. It's very difficult to study because we don't have any easy way to detect ultraviolet reflections like that. There are some cameras, but they're expensive and difficult to get. Glass blocks ultraviolet light, so it has to be anyway. There's lots of technical challenges to actually measuring ultraviolet reflection. But there's been quite a bit of work on it, and a lot of species do have really unique ultraviolet markings in their plumage.
So I think one more question for you, an important one that I saw come through and something that's on my mind as well. One of our viewers commented that they've seen news and research about birds moving their ranges further north or birds moving higher up in elevation to get away from seemingly the effects of climate change. What's been your experience watching birds, reading, researching, and thinking about birds in sort of this new climate crisis context?
Yeah, yeah, I've seen a lot of that in my 50 or so years of watching birds. A lot of species ranges are shifting north. Um, Here in New England, we're getting a lot of species are moving in from the south. Red-bellied woodpecker has arrived in my lifetime. Um, Tufted titmouse, cardinal, mockingbird were already common when I was a kid, but they've continued to increase and expand. Black vultures are just arriving in the last decade or two. Um, and also species that used to nest in Massachusetts are now only found farther north. Species that were right at the southern limit of their range here 30 years ago are now gone. The limit of their range is farther north. And I see, when I go north to the Arctic, I see big changes there in the places that I've been to over a couple of decades. Shrubs are getting taller. There's big changes going on. And it's hard to tell with some of the changes in birds' ranges. Species like red-bellied woodpecker, they're also benefiting from suburban landscapes and bird feeders, and they're found mostly in suburban habitats and less in the native woodlands. So it's partly a result of just the habitat changes that we've made. But there's definitely a climate aspect to it as well. And on top of that, birds arriving earlier in the spring, staying later in the fall. Um, uh, and there's definitely um, some species are going to lose out in the over the next 100 years. There will be species that can't keep up, that can't adapt, that their habitat disappears completely, and they're out of luck. But birds as a whole, birds are just so adaptable and so mobile. I think they will handle the changing climate probably better than we do. um,
So there's
it's
hope for birds.
Yeah, birds will survive. They are real survivors, and just so creative, adaptable, innovative, and mobile. They can just take advantage of any opportunity wherever it occurs, and find a new way to um, uh, make their way.
That's as good a way to wrap up as any right there. David, thank you so very much.
That's my pleasure. It was great to be with you, and
Uh,
happy to share all this.
So glad that you could join us for our virtual science cafe tonight. I want to remind everybody the name of the book is What It's Like to Be a Bird by David Allen Sibley. Look it up, go find it, get a copy, and tell us about it at the museum. You can follow the Museum of Natural Sciences on social media. We are on Facebook, Twitter, and Instagram as @naturalsciences. And make sure that you check out naturalsciences.org. The Science at Home page from our website right now is full of amazing activities, do-it-yourself science projects. When you've done all of the Zoom calls you can handle in a day, you can pick up a DIY science project or get some tips and tricks on going out and doing things like bird watching in your backyard. Maybe you pick up a Sibley field guide and you go look for some birds, even in your own backyard. So check out those resources. There's lots of great stuff that the museums put online, stuff that you can do right inside your homes, wherever you're at. We also have more great virtual live programs coming to you the rest of this week. Of course, the Science Cafe will be back next Thursday night as well at 7 o'clock on the museum's YouTube channel. We'll be talking with author Paul Bogert, who's going to talk to us about ecosystems and light pollution. So don't miss that one. That's going to be right here. If you want to get notified when we go live, you can like and subscribe to the museum's YouTube channel. That way you know when cool stuff is coming out from us. And have a great evening, everyone. Thank you for tuning in. Stay safe, and I hope we'll see you again real soon. Good night, everyone.